Welcome back, everyone. Ready for another deep dive? Today, we're taking on a topic that's, well, kind of terrifying and completely fascinating all at the same time.
Black holes.
You got it. We're going to be using a paper, Black Holes, a general introduction.
Interesting.
Yeah, it's by Jean-Pierre Luminet from back in February 1998.
Oh, wow. That's going back a bit.
I know, right? But trust me, this paper lays some serious groundwork even all these years later. It's like the Rosetta Stone for understanding these crazy objects.
I'm intrigued.
Well, Luminet makes this really cool analogy. He says trying to understand a black hole is like if, butterflies were trying to understand a flame.
Oh, I like that.
Right. Some flit around the edges, some get a little closer, well, you get the picture. Point is, these objects are just mind-boggling. But that's kind of what makes them so captivating.
Absolutely. The mystery is definitely part of the appeal.
So today, we're going to try to tackle some of the big questions. What are black holes? How do they form? What evidence do we even have that they exist? We're super lucky to have our expert here to help guide us through this cosmic maze.
Happy to be here.
So let's kick things off with the basics. What exactly makes a black hole a black hole?
Well, it all comes down to gravity.
Gravity, okay, yeah, but not just any gravity, right?
Right. It's gravity so intense that it traps even light.
Whoa, even light. Okay, now you're just messing with me.
No, really. It's a surprisingly simple concept at its core, though.
Hmm.
A black hole is just a region of space-time where gravity's pull is so strong that nothing, not even light, can escape.
See, you say simple, but I'm already feeling a little lost.
Well, this idea has been around for a while, actually. It was first proposed back in the late 1700s by John Michel and Pierre-Simon de Laplace.
Oh, wow, way before Einstein and all that.
Yeah, they use the concept of escape velocity, the speed you need to reach to overcome an object's gravitational pull. For a black hole, that escape velocity exceeds the speed of light, which, as we all know, is the universal speed limit.
Okay, so nothing can go faster than light, so nothing can escape a black hole. Got it.
Exactly. And this threshold, this point of no return, is defined by what's called the Schwarzschild radius. It's a formula that links a black hole's size to its mass. The more massive the black hole, the larger its Schwarzschild radius, and the stronger its gravitational pull.
Okay, that makes sense, but picturing light being trapped in space-time, like being warped, that's just mind-blowing.
Yeah, absolutely. Visualizing a black hole is tough. It's so outside our everyday experience.
Yeah, it's hard wrapping my head around it.
Well, physicists use this tool called light cones to help visualize it.
Light cones. That sounds kind of trippy.
Think of a beam of light expanding from a point. If you plot this on a graph with space on one axis and time on the other, you get this cone shape, and that's your light cone.
Okay, I'm sort of with you.
It represents all the possible paths that light can take from that starting point. In normal space-time, like what we experience, these cones are symmetrical.
Right, makes sense.
But near a black hole, where space-time is warped, the light cones get distorted. They tilt inwards towards the black hole.
So the black hole's gravity is pulling the light cones in.
Exactly. It's visually showing that extreme warping caused by the black hole's massive gravitational pull.
Okay, so those light cones are showing us how a black hole is bending the fabric of space-time.
Exactly. And we can even use light cones to picture how a black hole forms from, like, a dying star. Imagine a really massive star. It runs out of fuel, no more nuclear fusion to create that outward pressure, so gravity just takes over, and the star starts to collapse.
It implodes.
Yeah. And as it shrinks, its density increases, and so does its gravitational pull. Eventually, the star's light cones tilt inward completely.
Whoa, so the light can't even escape anymore?
That's it. That's the point of no return. The event horizon is formed.
The event horizon. That boundary around a black hole where nothing can escape. So anything crossing it, it's, doomed to fall into the singularity at the center. That point of infinite density where the laws of physics as we know them just break down.
That's exactly right. Once you cross that event horizon, there's no coming back. And then it gets even weirder. Time itself starts to get warped near a black hole. Luminet talks about this idea of, frozen time. He uses the example of an astronaut falling into a black hole giving a salute.
Time freezes. So, what happens to time near a black hole then?
Well, time is relative, right? Einstein taught us that. The stronger the gravity, the slower time flows. For a falling astronaut, time would feel normal to them. They'd keep saluting as they fall. But for an outside observer, watching the astronaut fall in, they'd appear to slow down as they get closer to the event horizon. Eventually, it would look like they're just frozen in time right at the edge.
So time literally slows down near a black hole. I mean, this is like something out of a science fiction movie.
Yeah, it's pretty mind-bending, but it's what makes black holes so fascinating. They really challenge our understanding of reality.
Right. And to describe all this warped space-time, mathematically, physicists use different coordinate systems. They're called metrics.
Right? Like the Schwarzschild metric?
Yeah, that one describes the space-time around a non-rotating, uncharged black hole. Then there's the Eddington-Finkelstein metric. That one helps us understand those light cones near the event horizon.
Right. They're both very useful tools for visualizing the structure of space-time near black holes.
Okay, so we've got these mathematical tools to describe them. But are black holes really just these giant cosmic vacuum cleaners sucking up everything in their path?
Well, they definitely have this powerful gravitational pull, but they're not exactly vacuum cleaners. In some ways, they're surprisingly simple.
Simple. I mean, they sound pretty complicated to me.
Well, black holes, unlike stars or planets, they don't have all those complex features. There's actually a theorem that describes this. It's called the no-hair theorem.
No hair. Okay, that's a unique way to describe a black hole.
Huh, it is a little whimsical, right?
Yeah.
But it's essentially saying that no matter what forms a black hole, a collapsing star, a gas cloud, even like a pile of old textbooks, only three things survive. Its mass, electric charge, and its angular momentum, or spin.
So all that other stuff, like the star's composition, its magnetic field, even the information in those textbooks, it's all gone.
It's all lost during the collapse. The black hole essentially shaves off all the details, leaving only those three fundamental properties.
So a black hole from a star and one from, say, a pile of textbooks, they'd be indistinguishable. If they had the same mass, charge, and spin, you wouldn't be able to tell them apart.
Exactly. And based on those properties, there are four main types of black hole solutions. Schwarzschild, which is non-rotating and uncharged. Reisner-Nordstrom, which is charged but non-rotating. Kerr, which is rotating but uncharged. And Kerr-Newman, which has both charge and rotation.
Okay, that's a lot of names to keep straight. But which one is the most relevant, I guess, for the black holes that we actually observe out there in the universe?
Well, in most astrophysical situations, black holes probably don't maintain a significant electric charge for very long. The electromagnetic force is much stronger than gravity, so a charged black hole would likely neutralize itself pretty quickly.
Oh, that makes sense. So what are we left with the Kerr solution then, the one that describes rotating black holes?
Yeah, that's the one that seems to be the most relevant for real-world observations. And those rotating black holes, they have this wild region around them called the ergosphere. Luminet describes it as like a cosmic maelstrom.
Oh, yeah, I remember reading about that. It sounds pretty intense. What makes the ergosphere so special?
Well, the ergosphere, it's a region outside the event horizon where space-time itself is being dragged along by the black hole's rotation. Imagine you're caught in a really powerful current. You're forced to move in the same direction, even if you're trying to swim against it.
Even if you're moving at the speed of light.
Yep, even then. And this swirling, it leads to something incredible. The possibility of extracting energy from a rotating black hole.
Wait, you can steal energy from a black hole? I thought nothing could escape those things.
It sounds crazy, right? But theoretically, yes. One method is called the Penrose process. Imagine you shoot a projectile into the ergosphere, and if you aim it just right, it splits in two. One piece falls into the black hole, but the other escapes.
So you're using the black hole's spin to fling that projectile out with more energy than it started with.
Exactly. It's like cosmic billiards. And the theoretical limit for how much energy you can extract this way is pretty impressive, something like 29% of the black hole's rotational energy.
29%. That's way more efficient than any energy source we have here on Earth. Black holes are sounding less like cosmic vacuum cleaners now and more like, I don't know, cosmic powerhouses or something.
They're incredibly powerful objects. And speaking of power, there's another surprising connection Luminet makes. It's the link between black holes and thermodynamics. I wouldn't have thought those two things had anything to do with each other.
Yeah, thermodynamics, isn't that like the study of heat and energy? Black holes are cold and dark. How do those two things even relate?
It is a little counterintuitive, but black holes, despite being cold and dark, they actually have properties that we can mathematically describe as temperature and entropy. And it turns out these properties are linked to the black hole's event horizon.
You mean the event horizon like has a temperature, an entropy. But isn't entropy like a measure of disorder or randomness? What does that have to do with a black hole?
It's a fascinating connection. The first law of black hole mechanics links the change in a black hole's mass to changes in its area, angular momentum, and charge. It really mirrors the first law of thermodynamics, which relates changes in a system's internal energy to changes in its entropy, volume, and other variables.
Okay, so there are some parallels there.
And similar to the second law of thermodynamics, which says entropy always increases in a closed system, the second law of black hole mechanics says that the surface area of a black hole's event horizon can never decrease. So every time a black hole swallows something, its event horizon grows.
So the area of a black hole's event horizon is like its entropy. Whoa, okay, that's pretty mind-blowing.
It is, and it gets even more mind-blowing when we start talking about quantum mechanics and something called Hawking radiation. But I think we'll save that for after the break.
All right, everyone, let's take a quick break and we'll be right back to dive deeper into the strange world of black holes.
See you in a few. All right, so where were we? Ah, yes, quantum mechanics and black holes.
Yeah, you were about to tell us about this Hawking radiation thing.
Right, so this is where things get really, really weird. It turns out that in quantum mechanics, empty space, what we call the vacuum, it's not actually empty.
Wait, what? Empty space isn't empty?
Nope. It's actually buzzing with all this activity, all these virtual particles popping in and out of existence. Virtual particles, what are those?
They're like these pairs of particles and antiparticles that they kind of just appear out of nowhere, and then they annihilate each other almost instantly.
So they're like fleeting blips of energy.
Exactly. And normally we don't even notice them because they disappear so quickly. But near a black hole's event horizon, something really strange happens.
Let me guess, the black hole's gravity messes with them somehow.
You got it. The black hole's intense gravity can actually rip these virtual particle pairs apart before they have a chance to annihilate each other.
So instead of disappearing, one of the particles gets sucked into the black hole.
Exactly. And the other one, it escapes into space.
Mm-hmm.
That escaping particle, it carries away some energy from the black hole. And that, my friend, is Hawking radiation.
Named after, obviously, Stephen Hawking, the brilliant physicist who first predicted this phenomenon.
That's right. And this radiation, it has a thermal spectrum, which means it has a temperature.
So black holes aren't completely black after all. They actually radiate energy.
They do. It's just incredibly faint. And the smaller the black hole, the higher its temperature and the faster it radiates.
So does that mean black holes can actually evaporate? Like completely disappear?
Theoretically, yes. If a black hole isn't actively feeding on new matter, it'll slowly lose mass through this Hawking radiation process. Eventually, over an incredibly long time, it could completely evaporate. But we're talking time scales far, far longer than the current age of the universe for typical black holes.
Okay, so the universe isn't going to suddenly be filled with exploding black holes anytime soon. That's a relief. But what about those mini black holes we hear about sometimes? The ones that might have formed in the early universe. Wouldn't those evaporate much faster?
That's a good question. Mini black holes, if they exist, they would have a much higher temperature than those larger black holes. So they could potentially evaporate within the lifetime of the universe, releasing a burst of high-energy radiation as they shrink and finally vanish in a big explosion.
Wow, that would be something to see. Have we ever actually observed anything like that, like a mini black hole exploding?
Not yet, unfortunately. Astronomers have been searching for signs of evaporating mini black holes, but so far, no luck. It could be that they're just incredibly rare, or maybe they didn't form in the early universe like some theories suggest.
So Hawking radiation, it's a really cool theoretical prediction, but we haven't actually observed it directly yet.
Right. It's a huge challenge for physicists to try to reconcile general relativity, which governs those large-scale structures, with quantum mechanics, which governs the behavior of particles at the smallest scales. Hawking radiation is right at the intersection of those two theories, and observing it would offer some major insights into how they fit together.
It's amazing how something as seemingly simple as a black hole can raise such profound questions about the nature of reality itself. And speaking of profound questions, Lou Monette talks about these incredibly intricate ways that mathematicians and physicists use to map the space-time around these mind-boggling objects. I'm talking about embedding diagrams, Kruskal diagrams, and Penrose-Carter diagrams. Have you ever worked with those?
Oh yeah, definitely. They're essentially tools to help us wrap our human brains around the concept of curved space-time around black holes. They use different coordinate systems and mathematical tricks to sort of flatten out the warped space-time so we can visualize its structure.
Okay, I vaguely remember hearing about those diagrams in my astrophysics classes, but to be honest, I'm a little fuzzy on the details. Could you give us a quick refresher?
Of course. So let's start with embedding diagrams. Imagine taking a slice of space-time around a black hole and then trying to embed it in a higher dimensional flat space, Like if you took a sheet of paper and curved it to represent the curvature caused by a black hole.
Okay, I can sort of picture that. What about those crystal diagrams? This always sounded kind of intimidating.
Crystal diagrams are particularly useful for understanding the causal structure of space-time around a black hole. They show us how light cones behave near the event horizon and help us visualize things like, well, black holes, obviously, but also white holes and even wormholes.
Wormholes, like those tunnels in space-time that sci-fi movies are always talking about, the ones that could maybe let you travel to other parts of the universe or even to other universes entirely.
Exactly. Although wormholes are still very much in the realm of theoretical physics, the mathematics of general relativity does allow for their existence. And Kruskal diagrams provide a way for us to see how they might connect different regions of spacetime.
Wow, that's pretty wild. So you're saying that it might actually be possible to travel through a wormhole. Where do I sign up?
Hold on a second. There are still a lot of challenges and unknowns surrounding wormholes. For one thing, they're thought to be incredibly unstable. Even the slightest disturbance could cause them to collapse before anything could travel through them.
Okay, so maybe wormhole travel is still a bit of a long shot. What about those Penrose-Carter diagrams? What do they show us?
Penrose-Carter diagrams are kind of like Kruskal diagrams on steroids. They use a really clever coordinate transformation that brings infinity into a finite region, allowing us to visualize the entire structure of space-time around a black hole in just one diagram. They're particularly useful for understanding the really complex structure of rotating black holes, like the Kerr black hole we talked about earlier. And these diagrams, they reveal some really mind-bending possibilities, like the idea of passing through a rotating black hole and ending up in another universe.
Another universe. Okay, now you're just messing with me, right?
I know, it sounds crazy, but the math of the Kerr solution does actually allow for this possibility. However, it's important to keep in mind that these are highly idealized solutions. In reality, black holes are probably much more complicated, and they might not allow for such exotic journeys.
Okay, so maybe interdimensional travel via black hole is still a little far-fetched. Fair enough. But let's get back to basics for a minute. We've talked a lot about the theoretical side of black holes, but how do we even know that these things actually exist? We can't see them directly, so what evidence do we have?
That's a great question, and it's one that astronomers have been wrestling with for decades. Since black holes don't emit light, we have to rely on indirect methods to detect them. And the most convincing evidence we have comes from observing the behavior of matter around black holes.
So we're looking for the effects of the black hole's gravity on its surroundings, like stuff getting pulled in and heated up.
Exactly. One of the most compelling pieces of evidence comes from those binary star systems where a black hole is orbiting a companion star. As matter from the star spirals inward toward the black hole, it forms something called an accretion disk, which is basically this swirling disk of superheated gas that emits intense X-rays.
So we're looking for these bright X-ray sources in binary star systems, and if we find one, that's a good sign that there might be a black hole there.
Exactly. And by carefully studying the orbital motion of that companion star, astronomers can actually measure the mass of the unseen object that's pulling on it. And if the mass is high enough, above the theoretical limit for a neutron star, then we have very strong evidence that it must be a black hole.
That makes sense. Are there any specific examples of these black hole candidates that astronomers have found?
Oh, there are quite a few. One of the most famous ones is Cygnus X1, a binary system located in the constellation Cygnus. Astronomers have been studying this system for decades, and they've determined that the unseen object there has a mass of about 15 times the mass of the Sun, which makes it a very, very strong black hole candidate.
Wow, 15 times the mass of the sun, and all that squeezed into a region smaller than our solar system. It's mind-blowing.
It is, and Cygnus X1 isn't alone. There are many other binary X-ray systems out there that are thought to contain stellar mass black holes, those black holes that formed from the collapse of massive stars.
So we've got evidence for these smaller stellar mass black holes, but what about those supermassive black holes that are thought to lurk at the centers of galaxies? How do we know those exist?
Well, once again, we have to rely on indirect observations. One of the key pieces of evidence comes from studying the motion of stars and gas clouds near the centers of galaxies. If we see stars whipping around an invisible central object at incredibly high speeds, we can use those speeds to calculate the mass of that unseen object. And in many cases, the masses are so enormous, millions or even billions of times the mass of the Sun, that the only plausible explanation is a supermassive black hole.
Millions or even billions of times the mass of the sun. That's just incomprehensible. Are there any specific examples of supermassive black holes that we know of?
One of the most well-studied supermassive black holes is the one that sits right at the center of our own Milky Way galaxy. It's called Sagittarius A, and it has a mass of about 4 million times the mass of the Sun.
Wait a minute, there's a supermassive black hole in our own galaxy that's both amazing and a little bit terrifying.
It is pretty amazing. But don't worry, it's not going to swallow us up anytime soon. It's incredibly far away, something like 26,000 light years.
Okay, that's good to know. So it sounds like we've got pretty solid evidence for black holes of all sizes, from those smaller stellar mass ones to those supermassive giants that live at the hearts of galaxies. It's incredible to think about the diversity of these objects out there in the universe.
It is, and there's still so much that we don't know about them. Black holes really continue to challenge our understanding of the universe and push the limits of physics.
And speaking of pushing limits, Luminet describes this pretty dramatic scenario where a star gets a little too close to a black hole, and let's just say things don't end well for the star. What happens when a star wanders into a black hole's gravitational grip?
Let's just say it's not a pretty sight. A star that gets too close to a black hole can experience something called tidal disruption. It's not a pretty sight. A star that gets too close to a black hole can experience something called tidal disruption.
Tidal disruption sounds kind of ominous.
It is. The black hole's immense gravity creates these incredibly powerful tidal forces. They stretch the star out
Stretch it out.
like a piece of spaghetti.
You're kidding.
Nope. Imagine this giant cosmic hand just squeezing the star, like from top to bottom, elongating it into this thin stream of gas.
So the star basically gets spaghettified.
That's one way to put it. It's brutal, but also kind of spectacular. This process releases a massive amount of energy.
I bet.
As the star gets stretched and ripped apart, some of the material falls into the black hole, but the rest gets flung outward at incredible speeds.
Like a cosmic explosion.
Yeah, kind of like a cosmic fireworks display, but with a lot more violence involved.
Mhm.
And astronomers actually observed these tidal disruption events.
Really?
Yeah, they see these sudden bursts of energy coming from galactic centers, and it totally lines up with what we'd expect to see when a star gets shredded by a supermassive black hole.
Wow, so we actually have observational evidence of stars being torn apart by black holes. That's wild. It's amazing to think that something that was once considered purely theoretical, like black holes, is now known to be a real and fundamental part of our universe.
It is pretty amazing. And we've come a long way in our understanding, too. Luminet's paper has given us a really good overview of these incredible objects.
Right, from those basic properties like their mass and spin to those mind-boggling implications they have for how we understand the universe as a whole, we've covered a lot of ground today.
We have, but there's still so much more to learn. Black hole research is constantly evolving.
Oh, absolutely. And with new telescopes and observatories coming online all the time, like the James Webb Space Telescope, we're bound to make even more groundbreaking discoveries. I'm particularly excited about the prospect of seeing those accretion disks around supermassive black holes in even greater detail. It's mind-blowing that we can actually capture images of those incredible phenomena.
Right. It's a truly remarkable time for astrophysics. And with the Event Horizon Telescope, we're not just seeing those accretion disks anymore. We're actually seeing the shadows of black holes themselves. Those regions where light just disappears.
It's like we're peering into the most extreme environments in the universe.
Exactly.
You know, it makes me think back to that question we were discussing earlier. What secrets would we unlock if we could actually journey into a black hole? Safely, of course. What could we learn about space, time, and gravity in those regions where, well, where our current understanding of physics just kind of breaks down?
It's a question that continues to fascinate physicists and astronomers. While actually traveling into a black hole might remain in the realm of science fiction for now, the theoretical exploration of these objects offers incredible insights into the fundamental nature of the universe.
It's mind-boggling to think about. And who knows, maybe someday we'll develop a theory of quantum gravity that'll finally unify general relativity and quantum mechanics. And then we might truly be able to grasp those mysteries that black holes hold.
It's definitely a goal worth striving for.
Well, I think we've done a pretty good job today of diving deep into the world of black holes, don't you think? We've explored their incredible power, the ways we can detect them, and all those mysteries that still surround them. We've learned about tidal disruption, Hawking radiation, and all sorts of other mind-bending phenomena.
Yeah, it's been a fascinating journey, and I hope our listeners have enjoyed it as much as we have.
I hope so too. And I hope this deep dive has sparked your curiosity to learn even more about the incredible universe we live in. There's always more to explore, more questions to ask, and more wonders to uncover. So until our next adventure together, keep looking up at those stars and keep wondering about the amazing cosmos that surrounds us.